I go. So let's start with the truncation error again. So local the local truncation error. So this is given by a function t of x, a tau of xt. This is just the equation x t plus delta t minus u of x t divided by delta t minus kappa x squared. Again, I'll have this on the lower line, minus kappa delta x squared u of x, did I say minus delta x of t minus 2 u of x of t plus u of x plus delta x t, like so. So then I briefly mentioned that we should assume that we're able to differentiate this tau, which means that we are going to do a Taylor expansion. So if we then first Taylor expand this bit, we will get that t of tau equals over delta t u of t plus delta t dtu. Yeah, all of these are going to be functions of x and t. So I just drop this, save us some time. dt squared u plus delta 3 d plus and then you have the minus u of x t again. So that's basically just this equation Taylor expanded, or not, well, this function evaluation Taylor expanded, minus kappa over delta x squared. So then we do the same with the second one, and we will get u minus delta x dt of u plus delta x squared dt u minus 3 dt 3 u, and then lastly 4. Yes, this is not faculty but factorial in English. So I've been saying it wrong most of the time. Somebody pointed it out. So in Norwegian it's fakultet, in English factorial. Yes. So for factorial. It actually has some nice history as well. It used to be called faculty in English as well in the, I don't know, 1800 or something. That doesn't really count anymore. Minus 2u, so that's this, and then we need the last one as well, expanded. So this is u. So again, oh, yes. Of course, this should be x. I haven't had enough coffee, apparently. And then if you want more stuff here, delta x dx u plus squared to factorial. Yeah, you see the structure. But I'm gonna make a point as well. plus, yep, x4 for factorial dx4 and u, and then of course you have more stuff coming down the line here. So quickly looking at this, you see that these two cancel. Again, this one, you see you have two positive u's and two negatives u there. So these cancel, and this one will also cancel. And these two will cancel, but these two will add up. So will these. So then we're stuck with, I'm using too much space now. Tau of xt equals u of t. Yeah, there should be a, let's see, 1 over delta t. No, because, no, wait. So we only have this, true. So then we're stuck with t dt of u plus delta t over 2 factorial twice time derivative plus, well, I just add this one as well, dt3u. So that's the first one, and then the next one we will have minus this kappa dx squared u plus delta x squared over 12, because 4 factorial, that should be 24, but we have 2 of them, so 12. X4 of u. But then if you take a look at our equation again, which says that dt of u equals kappa dx squared u, we see that these two cancel. So if you write this out, see that this one and this one cancel, so you're left with delta t over 2 factorial tu plus something which we don't really care about, minus kappa delta x squared over 12 dx for u plus something. So we see this is big O of delta t plus big O of delta x squared. So this explicit scheme is first order in time, second order in space. So when you're going to do this, you have to pay extra close attention to your time step. So usually you want your delta t to be in the range of delta x squared. So if this is 0.1, I mean if delta x is 0.1, then you would want delta t to be something in the order of 0.01. Just to preserve the error. Because if you have a very small delta x, but a big delta t, then this will be your error. Then it's no point in having a small delta x. And if you have a big delta t, then you and a small delta x, then yeah, it defeats the purpose. But this is an explicit scheme. There is a better scheme. It's not that much more difficult to implement. It's called the Crank-Nicholson method. And from what I heard, some of you have already had this method. So what you're doing, you see, crank Nicholson's method. So we improved the method by actually averaging the spatial derivative over 2 time steps. Which means that, well, again, you start with ut equals this kappa ux x uij plus 1 ij delta t. So then you will have 1/2 kappa of d2 uij plus d2 ij plus 1. So this basically means that you average over 2 time steps. So one where you add and the next one. And also, in order to save some space or writing, I would introduce R to be kappa delta t over 2 delta x squared. I see in the book they have defined a different R, so they will get slightly different equations. I mean, they look like slightly different equations, but it is the same equation, actually, or same matrix. Later, it's only that this R is defined slightly different. It's the 2. That's different. So if we then expand this, this is the central difference operator. So I need more space. Well, yeah, do you have to expand this again? Do you know how it goes? D. So, I mean, it's the same. Okay, so I just expand one of them. So, d2 uij equals, yeah, of course, uij minus 1 minus 2 uj ij. And then you should be able to see that if you just replace these j's with j plus 1, then you have this one as well. It's just that it's getting annoying to write all of these indices. So you have the plus 1. So if you just take plus 1, plus 1, plus 1, then you get this one. Plus 1. So then we can rewrite this, having all of the j plus 1 on one side and all of the j's at the other side. We will get minus r u I minus 1 j plus 1 plus 2 r u I j plus 1 minus r u plus 1 j plus 1 equal u I minus 1 j plus 1 minus 2 R U I J and plus R U I plus 1 and J. So there you see they have kind of a neat system. So we can easily write these in matrix form as 1 plus 2R minus R minus R plus 2R minus R, and of course 0 minus R plus 2R minus R 0 0, and then this one will just continue as I tri-diagonal band matrix, and we will end up with minus R plus 2R minus R minus R 1 plus 2R, and then U0 J plus 1 U1 J plus 1 und so weiter UN J plus 1 and then similar for this, minus 2R R 1 minus 2R R R 1 minus 2 R R R R R. Speak like a pirate, eh? U 0 J U 1 J U N J. And this matrix and vector can easily be multiplied, so you have like just a vector. So you can easily get this on the form. Let's see. If you call this matrix A, big B, and J. So then you have a, well, I need more space. Equals B U J. So this can easily be calculated because you have all of these values. You know how this looks like, so then you get a column vector. I suggest you do this on component form instead, though, instead of a matrix multiplication. And then you can easily solve this using, for instance, the conjugate gradient or successive over-relaxation or Jacobi or Gauss-Seidel. I suggest conjugate gradients, though. But we can also see that this is an implicit method because we need more of the points. We can't just isolate this on the left-hand side. Method. And again, we can write the stencil here. So this is going to be tj plus 1, tj, x I minus 1, xi plus 1. And you see we have this nice implicit stencil. Also, I'm not going to go through it, but it can be shown that the truncation error, it can be shown that the truncation error t of xt for this method is second order in time and second order in space, like so. So this is a more stable algorithm. So if you just briefly look at these, I mentioned that you should solve it with, for instance, Gauss-Jordan. No, conjugate gradients. Or Gauss-Seidel or the Jacobi. But if you do this with the conjugate gradient, you can actually solve this in linear time. So if you go back to the explicit equation, it looks a lot easier or a lot simpler to solve than this explicit version, not this implicit version. But when you start using these good algorithms, you will see that this one has approximately the same time to solve. So in linear time. So we have O(n) time, where n is the amount of grid points. So there's really no reason why you shouldn't use this, except that it's a bit hard to implement, but that's you just implement it one time and then you can use it many times over. It's also more stable than the implicit method. No, explicit. So and the reason why you can actually solve the system in linear time instead of quadratic time is because this is a sparse matrix, sparse tridiagonal matrix. I guess I should write this. So the implicit solver is as effective as the explicit one when it comes to runtime, at least. And we can also look at the stability of these methods. Stability, let's see. So for the explicit method, we need that kappa delta t over delta x squared be less than or equal to 1/2, at least. I mean, if this isn't fulfilled, then your system will just crash. You will just get a nonsensical solution for it. It will just either blow up or nothing will happen. Whereas the implicit one, and then especially the Crank-Nicholson's one, this is unconditionally stable. So you can, in essence, you can pick delta t and delta x, the the grid spacing, so to speak. You can pick it as you want, within reasonable limits, of course. I mean, you still have the Truncation error to keep track of. So for better accuracy, so for instance, if you want this r to be approximately 1, then we can try to pick, so if you want +1, and then remember that r equals kappa delta t over 2 delta x squared. Then we have to pick delta t to be over kappa, but that doesn't really matter in this case, because here you want them to be approximately the same order. So you see both of them are the same order, so if this is a lot smaller than delta x squared, well, then you will lose accuracy because your delta x is too big. Yes, I can try to show I think actually we'll have time to show an example, and then I can. So I've tried to implement this, but that's the explicit method. So then it's easy to just pick these such that everything goes to, well, hell. It just crashes basically. Be able to show this now. No, first we should first do the boundary conditions as well. So in this case, here the boundary conditions are just 0. So I've just elegantly skipped them. Just then you get this very nice matrix. But if you try to introduce boundary conditions as well, it will be slightly altered. I guess this is okay to remove. So yes. Since this is just a one-dimensional problem, well, in space anyway, then we see that for, well, with so we see that, did I write down my boundary conditions somewhere? Nope. There we go. So for this, we've basically said that u of 0 t equals u of lt equals 0. But this isn't general at all. So next we can look at, so I'll skip this, and we'll say u 0 t equals some kind of constant to the left, and u of, well, lt is some constant to the right. which means that our grid, so we'll have CL over there, CR at the other end, and then you will have U1, so on, and then at the end, UN, well, -1, I guess. So in the explicit solver, this is pretty straightforward. Explicits, you will have U1, J plus 1 equals U1, J plus this kappa, the T over delta X squared, U0, J minus 2 IJ plus 2. Well, this is going to be 1. But this one is just supposed to be equal to ZL. CL, so that's all you have to care about. And for the right version, you will have that UN minus 1, which is this point. J plus 1 should be 0?
U0?
This one?
Yeah.
No, that's kind of this point.
Yeah,
Yeah, so U0 isn't a thing. It's just the endpoint. So it just has this value. J plus kappa delta T X squared U of n minus 2 J minus 2 plus 1 J plus UN J. But again, this one isn't a thing, so it should be CR. So basically, if you want to do this, you just loop around these points, and then you just let the endpoints be, unless you change them with some kind of function instead. That is also possible. And for the Crank-Nicholson, it is similar. So if I just remove this, see, I'm just going to call this CN. You will have that for the left side, you will have minus R U 0 J plus 1 R U 2 J plus 1 equals R U 0 J plus 1 minus 2 R 1 J plus R 2 J. Again, you have to replace these. So this is going to be the left endpoint. And so is this. CL. And then for the right endpoint, you will have minus R U n minus 1 plus 1 to R U n well minus 2 minus n plus 1 so n I guess it's going to be see. No, this is going to be -1. This is going to be -2, and this is going to be -3. No, n. -1 and -2. R u n -1, j plus 1, plus 1 minus 2 r u n -1 j plus r u n j. Yes, it's supposed to be an r. And then again, you replace this one and this one, and you can solve for it. And you can also do this with functions, as I said. So this A matrix, so if you do this and you solve the system, this A matrix will look the same as it did again, because you see you get this one over to the right-hand side, since this one is just a constant right now. So then you will have 1 plus 2r of this u1, and you will have minus r of this. So that means we can basically just switch some indices here. So this will be 1, this will be 2, this will be n minus 1. And then you can calculate this, and that's what I've done here. So we will do this. Let's see, where's my sponge? So with boundary conditions, this A matrix will look exactly the same as, well, without boundary conditions, or the boundary conditions are equal to 0, only that we will now have, I'm going to do this in a general fashion, so we will have R times CL of time Tj plus CL time Tj plus 1 if they are time-dependent boundary conditions. This could be if you are gradually heating up something. For instance, plus, let's see, one minus 2r 0 j plus r u1 j, and then we start in a similar fashion, plus, so now we're away from the boundary conditions, u2 of j plus r u3 of j. And now the next one, you will just increment all of these values until you get to the last one, where you will get r u n minus 2j plus 2r u minus 1 j plus r c r of tj plus cr of tj plus 1. And then this one is, let's see, this whole thing is a column vector B times U J, like so. Does that make sense? Then I'll try to show just a small application of it. So this is part of exercise 0. So some of you should have seen it already. So here we solve the heat equation using the explicit method because it's a lot easier to explain. Again, this is just geometry. So I want a, so I'm in this example, we're cooking a steak. Our steak is 5 centimeters tall. We're using 100 grid points. The maximization time is 30 minutes with time steps of 0.1 seconds and some other constants. So this alpha, that's the thermal diffusivity of water. Because meat and water is the same, and this is, well, it's an assumption because it was hard to find a thermal diffusivity for steak. So that's why we used water here. Initial conditions, you say that the initial temperature of the steak is room temperature, so that's 20 degrees. The oven is 120 degrees centigrade, and the final minimum temperature, so this is also an example of a stop condition. So when you're the minimum temperature inside the steak is 60 degrees centigrade, then you stop the simulation. And as you can see, it's used with a very simple explicit method. So if we just run this, you see that the endpoints, they're constant at temperature 120, and just heat it up until the up until it has a core temperature of 60 degrees centigrade. And it also checks for this beta. So if I now have a large, let's see, large time step instead. So if I have 1 second time step, what does this give me? Yes. So here you see it just goes completely bonkers. See if I can actually stop this now. But yeah, you see when beta is more than a half, the simulation just breaks down. So I can try to start this again, and then you see it just begins, and then it just like, it's just crazy. So this is why you should try to avoid, there we go, explicit. And also you can have endpoints or boundary conditions that change during time. So here we are cooking our steak. The boundary conditions are the same, but then we take it out of the oven and let it rest for 5 minutes. And then we'll see that the temperature at the endpoint drops drastically. Let's see. And then 6 degrees, and then suddenly it drops. So then you can see when you let your steak rest for 5 minutes, you get an even temperature. But I've never made steak inside the oven before. So you can actually try to modify this, this code and have it in a skillet instead. So then you would have one of the endpoints would be the temperature of the skillet. The other would be, well, the ambient temperature. So there's a lot more you can do using this equation. The code here is already uploaded. So if you want, you can take a look at it. Yep. Guess that's it.